In Chapter 4, we'll be talking about atoms and elements, and in Part 1, we'll be looking at the parts of an atom and patterns that we see with different types of elements building up the periodic table. So, when we think of atoms, we tend to think of science, we think of chemistry, but we don't think about experiencing atoms. Well, this is one thing that the author points out in the very beginning of this chapter is a visit to the seaside and experiencing atoms, smelling things in the air, that seaside odor. Well, seaside air smells the way it does because of substances within the air composed of nitrogen and oxygen molecules, things called amines. So, for instance, the amine that he is showing here is triethylamine. This is a smell that is emitted by decaying fish. So this is the triethylamine right here. He also shows nitrogen molecules and oxygen molecules that make up the air. So we see the molecules in the air. We see the triethylamine from the rotten fish. Here he shows the structure of seaside rocks, which are composed of silicates. So these are silicon in the black and oxygen atoms in the red. So we experience atoms all the time, everything around us. And just another interesting thing, other things, the aroma of the seaside, more than just rotting fish. Sulfur compounds that are created by algae in the sea because of their enzymatic activity, or different compounds from different bacteria, hydrogen sulfide gas. We don't tend to think necessarily of these molecules when we smell that ocean air. Some people enjoy it, some people not so much, but we can break it down to the things that we experience. So when we're talking about atoms, we need to realize that we're talking about incredibly small particles. So for example, if we pick up a single pebble from that hypothetical shoreline, that shoreline the author was walking on, there are more atoms in that one tiny pebble than you could ever imagine counting. And then the number of atoms in that single pebble would be bigger than the total number of pebbles in the bottom of the San Francisco Bay. There's just so many of them. So to get an idea of how small an atom is, this is an example that he gives in the book. If every atom within that one small pebble were the size of just the pebble itself, so we have a pile of pebbles, that really tiny, not quite sand, but just a little bit bigger than sand that's at the bottom of the water there in the shore. The pebble, one tiny little pebble itself, would be larger than Mount Everest if every atom within the pebble were the size of the pebble. So that gives you some idea of the scope of what we're talking about, how small these objects are. So summarizing what we know about atoms. First of all, we've talked about matter. All matter is composed of atoms. The properties of the atoms determine the properties of the matter. So it matters what atoms we have in a substance. Okay, now this third one is included in the book, but I have a little bit of a quibble with that. An atom is the smallest identifiable unit of an element. Okay, I'm sorry. That one I don't have the quibble with. It's the next one. An atom is the smallest identifiable unit of an element. So if we break it down, that's the smallest thing we can get that still has the characteristics of that element. Okay, now the next one. An element is a substance that cannot be broken down into simpler substances. Well, that depends on your definition of a substance. It cannot be broken down into a simpler material that has known properties that we know of, but elements can be broken down into smaller particles. Okay, let's just leave it at that. There are about 91 different elements that occur naturally. So consequently, there are about 91 different kinds of atoms, again, that occur naturally. Now, we have more elements than that. If you look at a periodic table, you'll see it goes well beyond 91, and that's because scientists have succeeded in making elements. And we've got about 20 right now that we have made that are not found in nature. Now, some of those hang around long enough that we can do something with them. Some of them are very, very short-lived. So remember femto that we talked about as a unit? Femtoseconds. Some of these things have lasted. So not necessarily useful for anything other than the fact of saying that we have created it, but it leads to other discoveries. It leads to understanding of the properties of elements, and so that's why we try synthesizing these. Now, the exact number of naturally occurring elements, that 91, notice we say about. That's a little controversial because some elements that were previously considered only synthetic might actually occur in nature in very small quantities. We just haven't really found large amounts of them. So the 91 that we say occur in nature, those are things that occur in large enough quantities that we can kind of put our hands on it, if you will. So where did this theory that we have for atoms come from, the current atomic theory? Well, this came from Democritus, who lived around 460 to 370 BCE. So his mentor, Leucippus, from the 5th century, put him onto the idea of an atom. So Democritus theorized that if you keep dividing matter up, so you take something and you cut it in half, cut it in half, cut it in half again, keep going, you will eventually end up with a tiny indestructible particle. Now we know now that they're not indestructible, but that was the thought at the time. And his word for these indestructible particles was atomos, which developed into our word atoms, meaning indivisible. So this is the first recorded instance of the idea of an atom, of this indivisible particle, was with Democritus. Okay, so here we see a picture of Democritus with Diogenes. Okay, so as imagined by a medieval artist. So just theorizing the elements of the earth and these indivisible particles. Now it wasn't until 1808, over 2,000 years later, that we had a formalized theory of atoms from John Dalton, okay, that gained broad acceptance. Work had been going on for those 2,000 years, but not to the extent of putting it together. Okay, so what we currently base our modern knowledge of atoms on is Dalton's atomic theory. And there are 3 parts to that. Number 1 states that each element is composed of atoms, tiny little indestructible particles. Okay, we know that one's not true now, but we'll just keep going with that for now. His second postulate to his atomic theory is that all atoms of a given element will have the same mass and same set of properties to distinguish them from any other element. Okay, again, there's some slight differences, but overall that works for us. And then number 3, atoms combine in simple whole number ratios to form compounds. That one, absolutely, that one holds true for us. Okay. Now, the theory that was held about these atoms was that they sort of existed in just sort of a sphere of charge, that there were parts of an atom and they just kind of existed in this mass. Okay, so we're going to take a minute here and look at this video that talks about the original model of the atom that existed around the time of Dalton. This was J.J. Thomson, and he had this plum pudding model, and we'll learn what that is. Okay, so just an interesting little video from Veritasium. Again, I know time is at a premium, but if you ever have time, great videos to check out. They're great science videos. All right, so Thomson had his plum pudding model. Now, this plum pudding model came about because he theorized that there were actually parts to an atom. It wasn't just a solid mass of something. Okay, so his parts that he had were electrons, which were negatively charged particles. They were much smaller and lighter than the overall atom and the other parts of the atom, and electrons would be uniformly present in many different kinds of substances. So they would just be evenly spread throughout the plum pudding. Atoms would also contain a positive charge that would balance the negative charge. So in this model, just the red is kind of like the matrix of the plum pudding, and the electrons, the little yellow dots, would be like the plums or the cherries, or if you had a blueberry muffin, the blueberries inside of the muffin. Okay, so this was J.J. Thomson's model of an atom, but it was groundbreaking in that the theory was that there were actual parts to these elements, to these atoms. There were many scientists who wanted to prove J.J. Thomson's model of the atom, and one of those was one of his proteges, Ernest Rutherford. Now, in 1909, Ernest Rutherford set up an experiment known as the gold foil experiment now, in order to prove this plum pudding model. The idea was that he would have a source of electrons here. It's encased in lead. The idea is that this source would emit a beam of electrons, and they would strike a piece of gold foil that was put in the center. And then there was a detector placed around that piece of gold foil that would detect electrons as they passed through this piece of gold foil. Now, if the plum pudding model were to hold, then imagine, if you will, firing a bullet at a blueberry muffin. What do you expect to happen? You expect the bullet to basically go through that blueberry muffin. There's not a structure there to stop these stream of energy, so the bullet versus the stream of electrons and the energy involved in that. Well, Rutherford thought he was helping Thomson, but he subscribed to the theory of the plum pudding model, but what he found was actually quite the opposite, and it was absolutely stunning to him and to other scientists. So many of the particles did pass right through the foil, as expected, but not all of them. They didn't all just pass through here. Some of them got deflected slightly. Some of them got deflected at a very sharp angle, to the point where not only did it not go through the foil, it bounced back off the foil and struck the detector behind the foil, behind the beam here. It was commented once that this was so shocking to scientists at the time because it was like firing a bullet at a piece of paper and having it bounce back at you. It was thought that there wasn't a structure here to the gold foil in order to stop these particles, but instead there had to be something fairly massive there that was stopping that stream of electrons. Okay, so they were expecting these particles to go straight through, and instead, so here they might strike an occasional proton, occasional center, but most of them would pass right through. Instead, what happened was most of them passed straight through, except for a few that might angle off this massive nucleus, or might hit it and bounce backwards off of that. So a new model for the atom came out of Rutherford's gold foil experiment, the idea that we have a massive nucleus that contains those positively charged particles, or protons, that balance those electrons, plus neutrons. Neutrons are going to be particles that have mass. They add mass to the center of the electron, but they do not have a charge. So Rutherford's modification of the nuclear theory of an atom, the idea of, or his modification of the theory of an atom, the build of an atom, was to add the nuclear theory, to build a nucleus. So the idea here is that most of the atom's mass and all of its positive charge are going to be contained in this small central core called the nucleus of the atom. So most of the volume of the atom around that nucleus is actually just empty space, and in that empty space, those tiny negatively charged electrons are going to disperse. They're going to be found somewhere in that space around that nucleus. Sort of like planets are in the space around the sun. Now there's a difference. There's a true orbit to the planets. There aren't necessarily to the electrons. We'll be talking about that later, but for now you can think of those electrons as just hovering around that nucleus at some point. Okay. Now the number of negatively charged electrons that are outside the nucleus in the sphere is equal to the number of positively charged particles or protons inside the nucleus. So the entire atom is going to be electrically neutral. We're going to cancel those charges. We've got a negative charge to a positive charge. Those cancel each other out. Okay. Now, when you look at this image, this model on the right, the nucleus has been drawn greatly enlarged, and the electrons are being portrayed as actual particles, and you can see they look like they're pretty close in size to the ones in the nucleus. That is just to give a representation of that, but the electrons are actually dispersed through a huge volume, but they weigh almost nothing, and they're very, very tiny in size. So there are all sorts of models for that to kind of help describe it. One of the things that I've seen is that if you had a nucleus that was the size of a baseball and put it in the middle of a football field, the electrons would be smaller than, I believe it was a grain of rice or a grain of sand, and it would be at the outer edge of the football field. That would be the closest electron you would have to the nucleus. So it's very hard to give a visual representation of what's really going on there. But just know that the distribution of mass in the atom is not going to be evenly dispersed throughout the atom. Okay, so the nucleus is going to make up almost all of the mass, more than 99.9% of the mass of the atom, but it occupies only a fraction of the volume. There's a lot of empty space in an atom. The electrons are going to be distributed throughout a much larger region around that nucleus, but they don't have much mass. They are just energetic particles. The matter at its core is less uniform than it appears. So actually matter is made up of a lot of space. The amount of actual stuff in matter is very, very small. So if we were to take matter and compose it like we think of matter, so just pile the atomic nuclei one on top of the other like marbles without a lot of space in between, this would make an incredibly dense material. So for example, a single grain of sand that was composed of just solid atomic nuclei, the grains of sand did not have that space within their atoms. One grain of sand would have a mass of 5 million kilograms. Now remember, 1 kilogram, 2.2 pounds. So that's, about 12 million pounds in 1 grain of sand. Very, very dense if we could condense all the material down and get rid of the space. And this is interesting because this is what astronomers believe that black holes are made of, and neutron stars. They're composed of this kind of matter in which the space in between the particles, in between the nuclei, has collapsed, and the atoms have folded in on themselves and become this incredibly dense material. So here's something to think about. If a proton had the mass of a baseball, an electron would only have the mass of a grain of rice. Okay, so relative mass comparison here, baseball to a grain of rice. The proton, nearly 2,000 times the mass of the electron. So if we look at these particles that we're talking about, we look at their properties. We've talked a little bit about the mass. We want to look at electrical charge. We've talked about positive, negative, neutral. Okay, so what are we talking about here? Well, this is the electrical charge of these particles. It's a fundamental property of protons and electrons. And these charges, positive and negative, are opposite, but they attract. So we talk about opposites attract. That holds for these particles. So Now, at the same time, if we have two like particles, positive particles, bringing them together, negative particles will repel each other. It's like magnets, okay? And this is why magnets work, is because of this positive-negative interaction. It's actually a flow of electrons within the magnet that is set up. So for this case, positive is red, negative is yellow. These two attract each other. I try to put two positives together, two negatives together, they're going to repel each other, just like trying to put the same pole of a magnet together, a north to a north or a south to a south. Doesn't work. Okay, now the other thing is when I put a positive and a negative together and they attract, a +1 charge, a -1 charge right here, those are going to cancel each other out, so the two together give me a net 0 charge, also known as charge neutral. That's very important because when we look at basic elements, we're talking about charge neutral particles. All the positives and negatives cancel each other out. Okay, so to summarize the parts of an atom, protons and neutrons are going to have very similar masses. Okay, here's the actual mass of them here, 1.67, varies a little bit beyond that, times 10 to the -27th kilograms. Very, very tiny quantity. Okay, now we will look at the mass in terms of something known as an atomic mass unit as well. Okay, so an atomic mass unit is a little bit easier way to think about the masses of these materials as opposed to, kilograms, grams, things that we can weigh on a more macroscopic scale. So it has an AMU of about 1 for both a proton and a neutron. Charge of +1 on the proton, 0 on the neutron. Now we look at the electron. You can see here it's a fraction of the mass of the proton and neutron, 0.00091 times 10 to the -27th. Okay. Mass in AMUs, this one's about 1, this one is 0.0005, and charge of -1. So the mass is essentially negligible compared to the proton and neutron, but it's got that opposite charge. Very important to us. And just another interesting side note, how do we know that there's charge in matter? Well, electrical storms and lightning actually show us that. Okay, so matter around us is normally charge neutral, which is a very good thing, so that you're sitting there looking at your computer, holding your book, sitting in your chair. Nothing's oppositely charged, or nothing has an overall charge, so you're not being shocked by sitting there, by touching things. Equal number of positive and negative charges balancing out. But when you've got an electrical storm, what you're getting is a perturbation in the charge balance of matter. So we get a buildup of one kind of charge, which is a negative charge, buildup up in the clouds. Okay, there's a positive charge buildup on the ground. Okay, and lightning is the effect of equalizing that charge, positives and negatives trying to neutralize one another. So that's why lightning is attracted to things on the ground. It is looking for a way to release that charge buildup, that negative charge buildup in the cloud. All right, so we've talked about basic properties of any atom. Any atom of any material you can think of will have protons, neutrons, and electrons. So what is it that makes an element different? Why is a piece of copper different from a piece of zinc, from a piece of gold, or any other material that we can think of? Okay. Elements are going to be defined not by the fact that they have protons, electrons, and neutrons, but by the number of those. Elements are going to be defined by the number of protons. So what we want to do to identify an element is count the number of protons in the nucleus of the atom. That is the fingerprint for that element. That tells us what element we're looking at. If we had any other number of protons, then we're looking at a different element. Okay, so number of protons is going to be important for identifying an element, and that is known as the atomic number. Number of protons in the nucleus is atomic number, and we use the symbol Z to represent that value. So for example, if we look at helium balloons, helium nucleus will have 2 protons. If If I've got 2 protons, I always have helium. If I increase that number of protons to 13, that can never be helium, can't be anything but aluminum. The Z value for aluminum is 13. So if you look at a periodic table, and be aware you do have a periodic table in the front cover of your textbook if you have a physical copy of the book. If you have the e-book, there will be a graphic of the periodic table that you should be able to call up. There are tons of periodic tables out there, but they're all going to have the same basic layout. First of all, if you examine a periodic table of the elements, like the one shown here, you're going to see that it's just like reading a book from left to right. We're going to start here. We're going to read our way across. I go from 1 to 2. I get to the end of the line. I go to the next line. Here's 3, 4, 5, 6, and so on. And I'm just counting my way to higher and higher numbers. That number at the top, that integer number, is the atomic number. That is the number of protons in that element. The next thing you see is a letter or 2 letters. That is the chemical symbol that tells us the name of the element that we're looking at, and we will get to that. The next number that you see is going to not necessarily be an integer, it's a decimal number. That is the atomic mass of the element, and we'll look at that in section 4.9, so that is coming. And then sometimes it'll also have the name printed out, not always. Most chemists are willing to work with just atomic number, chemical symbol, and atomic mass. The numbers become important to us because the numbers are what define what element we're looking at. So if you show a chemist this symbol right here without the word, if you tell them there are 20 protons in there and the symbol is Ca, they know you're talking about calcium. This mass number will come in handy for doing some other work that we'll look at later. So you need to start becoming familiar with this periodic table of the elements. This is the alphabet for a chemist. This is what's going to make up our language, and so it's important to know this without having to look it up every time. Now that doesn't mean you need to know every element on the periodic table. I promise you I have no clue on some of the ones that are down in the lanthanides and actinides unless I kind of look at them. You give me a symbol, I can't necessarily give you the name or vice versa, but I do have a general sense of the elements that are there and what they're used for. Okay, the ones that we're going to see the most are the ones that are naturally occurring, and those are about the first 91 or so that appear on here. Now, I'm not going to hold your feet to the fire to know every one of those, but it is important to start getting to know those. So I would say right now you need to start, maybe like make some flashcards, whatever you need to do, and get yourself up to at least about, let's see, I'd say up to element 40 is a good start here, but if you can get your way all the way through this one up to element 54, and then we'll pick some of the others out through here that you know pretty well. You've probably heard of maybe cesium and barium. Platinum is one that you probably should know. Gold is one everybody loves. Mercury is one you'll need to know. Lead is one you'll need to know. Radon is one that we'll be taking a look at. So try to get yourself at least up to about 54 and then pick some others out here that are pretty common. Eventually you want to get comfortable with all of these elements on the periodic table. Okay. All right, so let's take another look at these names and symbols that are on the table. A lot of them, it's pretty easy to figure out where they come from. Chemical symbols are based on the English name of the element. So if you look at something like hydrogen, you can see that the symbol for that is H. That makes sense. It starts with an H. Helium. Okay, they couldn't just use H. That was taken by hydrogen, so they went with the first 2 letters, He. Carbon is C. Nitrogen is N. Oxygen is O. Fluorine is F. Pretty standard. But then you hit some of these weird ones like sodium. Its symbol is Na. Why in the world would we use Na for sodium? Well, that's because it comes from the original Latin name. That was the first name for it. The name for sodium in Latin is natrium, so we use Na as the symbol. Potassium is another one. The symbol for potassium, it's number 19 on the periodic table. If you look at that, Its symbol is K. Why in the world would we use K? Because the Latin word is kalium. So some of them may not make sense if you don't know that history behind it. And here's some other examples of ones that are based on either Greek or Latin names. So lead is plumbum, so that's where the PB comes from. If you think about plumbers and plumbing, that's where the word comes from, because plumbers used to use lead pipe to pipe water into houses, and that came from the Romans and the Greeks. Mercury comes from hydroargy. I can't even pronounce it. You can see it there, but Hg is where that comes from. There's a really good reason we use the word mercury now. Iron comes from ferrum, so you might hear the word ferric used fairly often. If you've ever heard of a farrier who puts shoes on horses, that's where that came from, because horseshoes are made of iron. So people who made shoes for horses were farriers. They used ferrum. Silver comes from argentum, so Ag. Tin comes from stannum, so that's where Sn comes from. And copper is from the word cuprum, so cupric, if you've ever heard of that, Cu. That's the symbol for copper. There are also a few elements that got their name based on either properties or places or different things like that. So for example, argon, it's a gas at the very right edge of the periodic table, comes from the Greek argos, which means inactive. It's a noble gas, and we'll be looking at that in a minute. Other elements are named after countries. So polonium was named after Poland, francium after France, americium after the US, United States of America. There are other elements that were named after the scientists that either discovered them or somebody was honoring a scientist for that. So there's one called curium that's named after Marie Curie, who actually discovered two new elements, polonium after her native Poland and curium for her. She won 2 Nobel Prizes for that work, which at the time was unheard of. No one had won 2 Nobel Prizes, much less a woman, so very amazing. Bromine originated from the Greek word bromos, which means stench. So the picture here at the bottom right is showing bromine vapor, which is a reddish-brown gas. It has a very strong antiseptic odor to it. It's a very strong smell that will actually burn the nasal passages. So that's where this stench or bromos came from. So let's look at that table, that periodic table, in a little more depth. Why is the periodic table shaped the way it is? Why does it look the way it does? Okay, so we're going to back up a little bit in history, and we're going to look at a Russian chemistry professor named Dmitry Mendeleev, who started noticing patterns to the elements. So based on his observations of what we knew about the elements at the time when he lived, he saw that instead of just writing the elements randomly, he could arrange them in an order of increasing relative mass. And when he did that, he started seeing trends or properties repeat themselves. They occurred periodically. So that's where our periodic table comes from, is that there's a repetition, just like you have an octave in music. So you have do, re, mi, fa, sol, la, ti, do, and then you start over again, you go to the next octave and the next one, but it's a repeat of that same kind of basic 8 notes up the scale. He noticed the same thing about these elements. Okay, now here's an example of if we just took these elements and put them in a line. In Mendeleev's day, you would just make a list of elements. Okay. What he started noticing was that he could compare properties. So that's what these colors mean in here, that it's a repeating of properties. So he gave this set of properties, here's a set of properties, here's one, here's one. He didn't have any of those. Okay, here's one, here, different set of properties, here's one. This one had the same kind of properties as this one over here, helium and neon. That's what those two are. Then he went to the next one. This is sodium. Sodium had very similar properties to this one over here, lithium, 3 and 11. This one, magnesium, it had properties very similar to beryllium. So we're starting to notice this repeat. Now, this one's kind of odd man out, but we've got this green, pink, orange, And then there's this blue, green, pink, orange, kept going up, blue, green, pink, orange. We're getting this repetition. So what Mendeleev did, and what we do now, is to arrange them in rows and columns so that we get the same sort of properties moving up and down a column. Okay, so what you're seeing here is pretty similar to what Mendeleev had for his first periodic table. This was about the list of known elements at the time. A lot of them had not been discovered yet. All right, so periodic law. It's basically just a summary of lots of different observations about the properties of elements. So Mendeleev's periodic law was based on careful observation of the properties of elements. Like any other scientific law, the periodic law was just a summary of observations made by many people, but it didn't really give a reason for that observation. Okay, you need a theory to be able to do that. The law is just saying, we've noticed this phenomenon happening. This seems to hold true. But why is it happening? Well, there's a reason for it happening, but for now we're just going to accept that it does happen, that there is a repeat of these properties. When we get to chapter 9, we're going to look at the theory behind that scientific law. Why does that pattern appear? Why can we put the periodic table the way we've got? So we'll look at the why in chapter 9. Sorry, hate to do that to you, but for now, just need you to accept it and move on with it. Okay, so in part 2, we're going to look at some of the properties of those repeating properties of the elements in those columns.